All right, class, and we're going to take a look at section 13.2, which talks about probability with complements and unions of events. So here we've got a complement of an event is taking, the definition is taking the, we actually did it in the last lesson, but you take the amount of 100% and subtract it by the probability of an event occurring, and you get its complement. In other words, if we add them together, it would add up to 1. So here, if we have the probability of something, and the leftover is 1 minus that. And again, down here, you see that they do add up to 1. So in other words, if the odds of me flipping a coin is 50% to get heads, the leftover amount of getting not heads would be 50%. If I added that up, I'd get 100%. Very basic example, but there it is. Here we go. The graph is showing the first-time voters classified according to their party affiliation. If we randomly select a person from this group, what is the probability that the person has a party affiliation? Well, you could actually add all this up, but basically all we have to do is say, well, right here this is saying that they don't have one, so we're saying what's the probability that you have one? Well, these are the only ones that don't. So all you have to do is take 100% and subtract 23.7%. Okay? And so, these are percentages, by the way. And if I actually subtract that, 100 minus 23.7, 100 minus 23.7, oops, it's supposed to be 23.7, and that gives me 76.1% of the voters have a party affiliation. Now, the other way you could do it is you could actually add these up, and you should get the same answer. Okay, so it's just a little bit faster way of dealing with it. Finding the probability through a complement, coin is flipped 5 times. Finding the probability that there is at least 1 heads. Well, what we're saying here is at least 1 heads. To not get 1 heads, you would have to get all tails. Well, there's only one way to get all tails, and so the probability of getting them all tails, so one way to get all tails so here the odds of that happening would be 1 out of, well, how many different ways can it happen? It'd be 2 times 2 times 2 times 2 times 2 different ways that this could have happened. So in other words, it's 1 way out of 2 to the 5th. And this is using our fundamental counting principle. At each way I could have heads, tails, heads, tails, heads, tails 5 different times because I'm flipping it 5 ways. And so it's 1 out of 2 to the 5th, which is 1 out of 32 ways to get all tails. Now, why am I dealing with all tails? Because this is saying, this is what I don't want to have happen. I don't want to get this. So basically, what's the chance of that not happening? You want to take 1 and subtract 1 out of 32. Which you could do this way. 1 minus 1 out of 32. 1 is 32 over 32. Old school fraction basics. Minus 1 out of 32 gives me 31 out of 32. This is the amount of ways to not have all tails happen. So if this is not all tails happening, so this is not all tails, that's also called at least 1 heads. Not all tails means at least got 1 heads, and it's a 31 out of 32 chance of that happening, which is 31 divided by 32, which is a 96.8, almost 97% chance of that actually happening. So this is using complement. It's a much quicker way, but it's pretty much the easiest way to do this problem. And by the way, here's my notes, basically step-by-step. Find the sample space, probability of not getting heads is what I did, and then the complement is at least 1 heads. That's what we just did. So rule for computing the probability of a union of 2 events, you're going to see this notation actually in your notes, but or in your assignments on the lab, but here's the formulas. And so we select a single card from a standard 52 card deck. What is the probability that we draw either a heart or a face card? And so we're going to take a look at what this actually is doing. And so we've got hearts. These are all the hearts. And then these are all the face cards. Notice, by the way, aces are not included. I've always thought that aces were a face card, but they're not. It's just Jack, King, Queen are face cards. And here, our job is to do the OR, which is a union of hearts and face cards. So the probability of getting hearts is there's 13 out of 52. Probability of getting a face card, well, there's 12 in the whole deck out of 52 because there are 3 in each set and there's 4 sets. And then you have to subtract the overlap because we don't want to count this twice. If I add this here, basically I'm counting all the face cards twice. So I'm subtracting these 3, by all I mean the 3 hearts. I'm going to subtract the 3 out of 52 that are hearts, that are face cards that I counted already twice, and then that'll give me my, so you see that math happening over here. So I take my 13 plus my 50, or plus my 12, and then I subtract the face cards that are in both sets. Basically, if I add these here and then add them again here, I just added them twice. So I'm just cutting out the fact that I counted them twice, and it leaves it to actually only adding them up once. And then that gives me a total of, well, 22 out of 52, which adds up to 11 out of 26 is my chances of this happening. 11 out of 26 is basically a 42% chance that this would actually happen. Okay, so this is using the formula. It's basically probability of the first thing happening plus probability of the second, and then you're subtracting any overlap. Okay, and that's the upside down U means intersection. If you forget from a few weeks ago, actually, overlap is intersection. Okay, it's basically the and. Okay, here we go. So this formula, if we're given different parts of it, we can solve for the others. In fact, we're going to be. We have problems that are specific like this. We know the union of something, and then we know just one of the probabilities. And the second, we want to know, well, what's the overlap? Well, if I know the union and I know the individual probabilities, what I can do is use this formula here, and they're not A and B's, but I can make it that way. A, B, and then A, B again. Basically, I can replace them in this formula and put the 0.75 here, the 0.45, the plus sign, the 0.6, and then the minus, and then we'll just say X because we want, rather than write all that out, but I could write all that out. Anyway, I'm trying to solve for X. I'm trying to solve for this leftover part. And so we will. So let's go ahead and do that. So we got 0.75 equals 0.45 plus 0.6, and then minus, I'll actually write it out this time, P, A intersection of B. And so our job is to get this completely by itself. To get that by itself, we need to go ahead and combine some like terms. And here we add those together. So 0.45 and 0.6 is going to give us 1.05. And then we're just going to subtract that to the other side. And if I do that, I've got, so subtract the 0.75 here. So we've got negative 0.3 on the left side equals negative P of A intersection of B. And here, if I just divide by a negative on both sides, it turns it positive. And my probability then of the intersection is 0.3. So it's just dealing with a little bit of algebra to solve for the other missing piece. So if I actually work this out, put a 0.3 right there, I'll get 0.75. So we have one more like this. Let's take a look. And this time, we're trying to find the probability of A. So we've got the union, so 0.6 equals, we're missing probability of A, and then plus probability of B is 0.45. The intersection is 0.2. So if I set it up using the formula above, now I can just solve for probability of A. So I take 0.45 and subtract 0.2, so I get 0.25. If I subtract 0.25 from both sides, so this adds up to 0.25. If I subtract 0.25 from both sides, I'll get, so 0.6 minus 0.25 gives me 0.35 is equal to my probability of A. Okay, so this canceled out. That's subtracted to be 0.35. So that basically is how you do your, just an algebraic problem. You set it up in this order and then solve for the missing part, and that'll give you those problems. Here we've got a representative of all consumers who watch TV. We were looking for a consumer randomly. What's the probability that the consumer shops on the internet and oh sorry, I said TV, the income above $60,000. So this is, I missed the list of what our chart is that we're looking at, sorry. So annual income and then the hours that they, saying TV, but it's shopping on the internet, 10 or more hours. So what's the probability that the consumer neither shops on the internet nor has an annual income above $60,000? So it's a very interesting wording on the question. And so what we're looking at here is we're trying to figure out what's this space right here that has the overlap, because this is both 10 and has an income above 60,000. So basically we're saying neither nor. So neither T nor A is the complement of the union of them. So neither nor is the complement of the union. Okay, so let's work with that. So if I figure out the union, then I can figure out the complement. I just take 1 minus that. So here the union is found by taking our formula, which, so we'll just do the whole union here. So probability of, we'll call it T union A, like we have over here. So to find this whole union, what we need to do is figure out what's the probability of T happening. It's the 480. So it's the 480 out of the total 1600. And then we need to add it to the 496 over the 1600. And then we got to subtract this overlap that basically we counted here, and we again counted it that way. So we got to subtract the 192 out of the 1600. Okay, so if I do that, I'll just take the 480, add the 496, and then subtract the 192. That gives me 784 out of 1600. So divide this by 1600. And that's my 0.49 that you see down below. So these are just broken down into decimals rather than being left as fractions. But anyway, this 0.49 is right here. So our job is we wanted neither nor, and neither nor means I take this probability of both and subtract it from 1. It's basically saying I want the complement. So the answer to this question is 1 minus 0.49, like I've written down here, which is this 0.51 as my final ultimate answer to this particular question of neither nor. So 0.51. So neither nor means you have to go through the steps. So 0.51. Find the union of the two sets that they're asking about, and then you get the complement. It'll give you neither nor. Okay, and that's I think the clearest way is the way that this is written down right here. All right. So if you have any problem-specific questions, please email me through the Ask My Instructor feature of the lab.